December 7, 1941. Pearl Harbor burns, and within 72 hours, the United States military faces a logistical nightmare that has nothing to do with battleships or bombers. Across the vast Pacific, from the Philippines to Wake Island, American forces sleep under canvas tents that dissolve into rags after 3 weeks of tropical rain. In the War Department's morning briefings, field reports pile up like bad omens. Entire supply depots washed away by flash floods. Ammunition ruined beyond use. Soldiers hospitalized with pneumonia because their shelters literally collapsed in the middle of a downpour. Traditional wooden barracks aren't an answer either. They demand skilled carpenters. Weeks of labor and timber that doesn't exist on remote coral atolls. The Navy's projections are grim. 18 months to build proper housing for the men they need to deploy right now. In Washington, Brigadier General Eugene Raybould stands before a crisis table buried in weather maps, logistics charts, and construction timetables. His engineers face an impossible equation. They must design structures that can be manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who have never held a wrench, and still survive everything the Pacific can throw at them. 130-degree heat, Category 5 typhoon 6-hour monsoons, dumping 15 inches of rain, and the very real threat of Japanese bombers overhead. A standard army tent costs $12, but lasts barely a month in the jungle. A wooden barracks costs $8,000 and takes 6 weeks to build. Neither option works when you're island hopping across the Pacific and need shelter for 50,000 men yesterday. The British, fighting longer and bleeding in the deserts of North Africa, have already discovered one possible clue. Since 1916, they've relied on Nissan huts, semicircular steel shelters invented by Canadian engineer Peter Nissan. During World War I, these corrugated iron half-cylinders can house 30 soldiers, require no skilled labor, and shrugged off sandstorms with ease. But what works in Libya becomes a disaster in the Pacific. The British design uses heavy steel panels that need lifting equipment, and a ventilation system suited for desert dryness, not Philippine humidity. Inside, they become steam cookers. Worst of all, each hut requires custom foundations, concrete slabs, or wooden platforms, which brings the problem right back to carpenters and materials that don't exist. Raybould's team crunches the numbers, and the result is brutal. They need shelter for 2 million personnel across hundreds of islands. At conventional construction rates, the war would end before half the troops ever had a roof. Soldiers write home about waking up with boots full of rainwater, about mold growing on their uniforms overnight, about tents collapsing in the storm while they scramble through the mud at 3 in the morning. The Medical Corps warns that in some sectors, respiratory infections are hospitalizing more men than enemy action. This isn't about comfort anymore. It's about survival, keeping a fighting force alive long enough to actually fight. So the call goes out to America's engineering firms, university research labs, and the Navy's own construction battalions. The specifications sound like something out of science fiction. Build a structure lighter than a Jeep, small enough to fit on a single rail car. Needing no foundation, assembled in a single day with basic tools, costing less than $1,000, able to survive conditions that destroy permanent buildings, and of 10,000 units ready to ship in 6 months. In the tropics, nature doesn't just rot wood, it devours it. Fungus eats straight through preservatives and paint within months. Humidity doesn't simply make things damp. It corrodes metal fasteners until entire roofs cave in. Insects arente, merenuisances. Carpenter ants can hollow out a support beam in a single season. The British field reports read like horror stories. But to the Quonset team, they serve as a sacred checklist of everything that must be engineered out of the design from day one. No wood touching the ground. All steel, hot-dip galvanized, not just painted. Ventilation strong enough to prevent condensation. Every fastener accessible and replaceable without tearing the structure apart. By April 1942, the hybrid vision finally crystallizes. Take the Nissan Hut's elegant arch geometries, strip away everything heavy and vulnerable, merge it with Fuller's mass production philosophy in America. Industrial muscle, then design it to survive the specific Hella Pacific Island warfare. April 15th, 1942. Otto Brandenberger steps into a warehouse at Quonset Point, Rhode Island, with 30 engineers and a deadline so impossible it would be laughable if the war weren't so desperate. 60 days to design, prototype, test, and approve a building system that doesn't yet exist. The team works in shifts around the clock, sleeping on cots pushed against the walls, running on Navy mess hall coffee and adrenaline, the kind of pressure that either produces genius or collapse. Brandenberger divides his crew into specialist units. One team focuses on aerodynamics and load bearing. Another tackles how to nest the components for efficient shipping. A third works exclusively on the joint and fastener problem that plagued the British huts. The first radical decision arrives on day 3. No more waiting for perfect blueprints. Traditional architectural drawings take weeks, and they don't have weeks. Instead, they build in real time, sketch a detail in the morning, fabricated by afternoon, test overnight, release at dawn. Today we call it iterative prototyping. Standard practice in 2025, but in 1942, it's revolutionary. Buildings were meant to be designed on paper first, not hammered together in real-time experiments. The warehouse floor becomes a laboratory of metal scraps and ideas, a battlefield of failed joints, dented panels, and evolving prototypes. Borrowing a trick from aircraft manufacturing, every part receives a number, every revision is documented, and nothing moves forward until the last failure is fixed. Dimensions are dictated by cold practicality, not aesthetics. 16 feet wide, the maximum that fits on a standard railcar without special permits. 20 feet long per section. Short enough for 4 men to lift, long enough for functional interior space. When assembled, it forms a 48-foot-long structure, housing 36 men in bunks, or convertible into offices, medical stations, or supply depots. The Quonset team discovers this size as a sweet spot in structural engineering. Make it smaller and shipping becomes inefficient. Make it larger, and the panels grow too heavy for field assembly or require interior supports, undoing everything they were trying to achieve. The arch radius becomes a project's obsession, consuming 2 full weeks of the 60-day deadline. Too flat, and the wind would peel the building open like a sardine can. Too steep, and you waste headroom while creating awkward end walls. The final solution: an 8-foot radius, a perfect semicircle, offering 7 feet of headroom at the sides. Engineers call it a self-bracing arch. The corrugated steel naturally holds its own curve, allowing panels to be thinner, lighter, yet stronger than flat sheets. Load tests show the design can theoretically handle snow up to 40 pounds per square foot and winds exceeding 100 miles per hour. But theory means nothing against a Pacific typhoon. By day 40, the first full prototype rises a Frankenstein's monster of riveted panels, experimental bolts, and borrowed parts. 6 sailors, given just 4 hours of instruction and a box of hand tools, assemble it in 14 hours. Promising, but still not fast enough. The Navy's requirement is single-day assembly because once Marines hit a beach, they can't afford to wait. The bottleneck reveals itself instantly. The floor. The team had tried to include a wooden base, but it slows construction and rots in the tropics anyway. The fix is elegant: eliminate it entirely. The hut sits directly on the surface, whether coral, sand, dirt, or gravel. If a floor is needed, it's added later as a separate project. The core shelter must stand on its own. That single decision cuts assembly time to 8 hours and reduces shipping weight by 1,200 pounds per unit. June 10th, 1942. The final prototype stands complete. 96 corrugated steel panels, each under 50 pounds, bolted together to enclose 720 square feet of space. Then comes Judgment Day. Navy structural engineers arrive armed with wind tables, Pacific typhoon data, and the kind of skepticism only experience can bring. These aren't lab conditions. Their data comes from real storms. Typhoon Gloria slammed Guam in 1940 with 140 mile-per-hour winds, gusting to 180. The 1935 Labor Day hurricane that killed 400. In the Florida Keys hurled wooden planks through palm trees like javelins. If the Quonset Hut fails, it's not just lost property, it's lost lives. Brandenberger's team starts with the physics of the arch itself. When wind hits a flat wall, it creates maximum pressure, but a curved surface deflects it upward and around, dispersing that force instead of absorbing it. Before we dive in, take a second to like this video and subscribe. It helps bring forgotten moments of engineering genius back to life. Now, think of how water flows around a river stone instead of crashing into a dam wall. The semicircular Quonset profile works the same way. Hurricane force winds don't strike it head-on. They glide over it. The corrugations add another layer of brilliance. Those ridges running lengthwise give the panel strength, just as folding a piece of paper makes it stiffer than when it's flat. Each corrugation acts like a miniature I-beam, resisting bending forces that would crush smooth sheet metal. The physics gets fascinating when you trace how the loads move through the arch. In a normal rectangular building, the roof presses down on the walls. The walls press down on the foundation, and the entire structure depends on those vertical load paths staying intact. Strong winds can literally lift the roof off because it's a separate element resting on top. The Quonset arch changes the equation entirely. It's a single, continuous curve. Every panel shares its load with the next. Engineers call this a compression ring, the same principle that lets stone bridges stand for centuries without mortars. The hoop stress, the sideways force trying to spread the arch apart, is absorbed by the ground itself. Each Quonset panel is bolted to its neighbor with 3/4-inch steel bolts spaced every 6 inches, creating what? Effectively a 48-foot steel cable bent into an arch. But theoretical strength means nothing until it's tested. So the Navy designs a series of validation trials that border on brutal. At WWII, Rhode Island, they build a full-scale Quonset hut, instrumented with strain gauges, pressure sensors, and deflection meters. And then they wait for a storm. March 3rd, 1943. A nor'easter slams the coast with 75 miles per hour. Winds and heavy snow. Perfect test conditions. The gauges record the structure flexing less than 2 inches at its crown before snapping back to shape when the winds die. No leaks, no structural failures. The joints hold perfectly. The Quonset behaves exactly as the math predicted. Thrilling and slightly terrifying, because now thousands of soldiers' lives will depend on it. But the tropics pose a different monster. You can't simulate years of jungle humidity in a Rhode Island warehouse. So the Navy ships a test unit to the Panama Canal Zone, where humidity averages 85% and temperatures rarely drop below 80 degrees. 6 months later, the report arrives. Minimal corrosion on the galvanized steel. No structural degradation, but one big problem. Condensation. When hot, humid air hits the cooler steel at night, water literally rains from the ceiling inside. The fix demands clever simplicity. Ventilation. Louvers at both ends and along the ridgeline. Openings that let hot air escape while keeping rain out. The modification adds $47 to the cost, but it transforms the hut from a steel sauna into a livable shelter. The final engineering riddle. The foundation. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete? The answer comes straight from tent design. Giant steel stakes driven deep into the ground, connected to the base with adjustable tension cables. On harder surfaces, the team creates a bolt pattern that mounts directly to wooden sleepers or pierced steel planking. The beauty of the system is its flexibility. It moves slightly with the ground instead of fighting it, preventing cracks or tears. June 1942. The War Production Board gives final approval for Quonset Hut manufacturing, and what follows is American industry at full wartime throttle. The Navy signs contracts with 10 major steel fabricators across the Midwest and Northeast, companies that just months earlier were making grain silos and water tanks. Strand Steel Corporation converts its entire Penrose plant outside Philadelphia to Quonset production. George A. Fuller. Construction takes over an old auto parts factory in Chicago. Great Lakes Steel dedicates to rolling mills solely to corrugated panels. By August, these plants are churning out 1,500 huts per week, and the number keeps rising. The production line borrows heavily from automobile assembly logic. Massive steel coils arrive by rail, each 4 feet wide, enough for 30 panels. Rolling machines form the corrugations, ridges spaced precisely 2.67 inches apart. The process work hardens the metal, strengthening it beyond its original state. Next comes galvanization. Each panel is dipped in molten zinc at 850 degrees Fahrenheit. This isn't paint, it's a metallurgical shield. The zinc sacrifices itself to corrosion before the underlying steel can rust. In the salty Pacific air, that difference means a 5-year lifespan versus 50. The extra step costs $112 per hut, but quickly proves non-negotiable after early field tests show ungalvanized steel rusting through in 8 months. Every complete hut kit is packaged with almost obsessive attention to logistics. The 96 corrugated panels nest together like stacked bows, reducing their height from 8 feet to just 14 inches. End walls. Plywood with pre-cut doors and window openings, packed flat between the steel sheets. All fasteners, bolts, and tools go into one wooden crate, complete with illustrated assembly instructions designed for men who might not even read English. Each entire Quonset kit fits neatly on a single 40-foot flatbed rail car, ready to roll straight to the docks, the front lines, or wherever the Pacific demanded shelter next. This packaging density isn't just clever, it's essential. Every train bound for the West Coast is packed with either Quonset huts, ammunition, rations, or vehicles. There's zero tolerance for wasted cargo space. The logistics choreography becomes a masterpiece of wartime precision. Trains roll out of Philadelphia and Chicago daily, bound for San Francisco, San Diego, and Seattle, where Liberty ships and cargo freighters wait at the docks. Longshoremen load complete Quonset kits into ship holds, using the same cranes designed for tanks and artillery. A single Liberty ship carries 200 huts, shelter for over 7,000 men. The War Shipping Administration tracks every crate, every bolt, because these huts aren't just buildings. They're strategic assets. A shipment sent to Guadalcanal in September could be housing a bomber crew by October. The difference between operational aircraft and exhausted pilots sleeping in the mud. And it's at the receiving end where the Quonset design truly proves its genius. The Navy-esque construction battalions, the legendary Seabees, develop standardized assembly routines so efficient they look choreographed. 6 men, 8 hours, 1 completed hut, ready for occupation. It begins with site prep. Level the ground, clear vegetation, maybe spread a gravel base if available. 2 men handle the end walls. Wrestle the curved panels. Each panel overlaps 6 inches and bolts in with those 3/4-inch fasteners. No welding, no concrete, no carpenters, just wrenches, a level, and illustrated instructions, simple enough for any crew to follow. The record goes down on Espiritu Santo in January 1943. 4 hours, 17 minutes. A complete Quonset hut raised from bare dirt to livable shelter. But that's not the real victory. The real miracle is scale. 5 or 6 huts per day, per crew, across hundreds of islands. Entire bases appear faster than enemy bombers can destroy them. By December 1943, production hits 8,000 units a month. The logistics network hums so efficiently that huts ordered in Pennsylvania reach New Guinea in just 40 days. Including cross-country rail transport and an ocean voyage. The math tells the story of victory. 1 Quonset hut shelters 36 men for $1,394 in materials and about 60 man-hours of labor. A conventional barracks costs $12,000, takes 6 weeks, and needs skilled carpenters. The Quonset delivers the same function at 1/10 the cost and in 1/20 the time. By mid-1944, over 160,000 units have been deployed across every theater of war. Housing capacity for nearly 6 million personnel, all built in under 2 years. Guadalcanal, August 1942. The first combat-deployed Quonsets arrive on a beach baking under 95-degree heat and 90% humidity. Japanese bombers strike daily, turning anything resembling an American structure into smoking craters. Marine engineers unload the flat-packed panels under sporadic artillery fire, bolting them together in a coconut grove still scarred from last week's shelling. Within 12 hours, 10 new huts stand at Henderson Field, sheltering ground crews for the battle-worn F-4F Wildcats. 3 days later, a 500-pound bomb lands 40 yards away. The blast flattens palm trees and shreds nearby tents. But the Quonset flexes, ripples, and holds. When the dust clears, it's still standing, every man inside shaken, but alive. The jungle, however, proves just as dangerous as the enemy. Within 2 weeks, rust streaks crawl down every ungalvanized fastener. The salt air eats standard bolts like acid. Mold blooms across the interiors, transforming the huts into living art exhibits of green and black decay. The ventilation louvers that worked fine in Rhode Island can't handle the suffocating Pacific heat. Marines adapt on the fly, propping doors open 24/7, cutting extra vent holes with tin snips, ignoring the manuals just to survive the humidity. These improvised field fixes get reported back to Quonset Point, where engineers update the next production runs. Bigger vents, more louvers, and every single bolt galvanized, no exceptions. Iwo Jima, February 1945. A different kind of hell. Black volcanic sand that grinds into everything, no topsoil for stakes, and artillery raining down from Mount Sur. The Seabees land on D+2 and start assembly under fire, literally bolting panels together while mortar shells fall 200 yards away. The sand is too loose for normal anchors, so they improvise. Fill empty oil drums with sand and tie them to the base cables. In March, a Pacific typhoon tears through, with winds topping 110 miles per hour. The oil drum anchors hold. The Quonsets survive. Wooden structures vanish. The base commander's report to Pearl Harbor is brutally simple. Quonset Hut survived, everything else gone. The Arctic brings the opposite challenge. In the Aleutian Islands campaign, Quonsets are deployed at Dutch Harbor and Adak, where winds exceed 100 miles per hour and temperatures plunge to 40 below zero. The code turns steel brittle, and early models crack around bolt holes. Engineers respond fast, specifying cold-rolled steel alloys for Arctic kits and adding rubber gaskets at every joint to absorb stress. Heating the huts brings another surprise. Warm air meeting frozen metal makes it rain inside. Crews adapt again, installing insulation blankets and keeping ventilation running, even in sub-zero weather. By winter 1943, a new generation of weatherized Quonsets emerges: double-wall construction, internal insulation, and airflow systems that preserve heat while managing condensation. From jungle to ice, the hut evolves with every battlefield it faces. North Africa and Italy bring entirely new challenges. In Palermo, Sicily, a Quonset hut, repurposed as an ammunition depot, takes a direct hit from a German 88mm artillery shell. The shell pierces the corrugated steel, detonates inside among crates of small arms ammunition, and the explosion should, biologic, vaporize everything. But it doesn't. The curved arch channels the blast outward, venting energy through the walls and roof. The frame ends up twisted, but standing. Explosive ordnance teams examining the wreckage note that a normal rectangular building would have collapsed instantly, trapping anyone nearby under rubble. The Quonset-S continuous compression ring saves lives, proof that even catastrophic failure doesn't mean total collapse. Then comes the Pacific typhoon season of 1944, the ultimate test. Super Typhoon Cobra slams the Philippines in December with winds over 140 miles per hour and a 20-foot storm surge. At Tacloban, 80% of all structures are wiped out. Wooden buildings explode into splinters. Concrete blockhouses crumble as their foundations erode. Out of 43 Quonset huts on base, 39 survive completely intact, and the remaining 4 suffer only repairable damage. Bent panels, torn seams, but still standing. When Navy engineers study the survivors, they find the deciding factor is anchoring. Huts with proper ground attachments ride out the storm. Those with makeshift or lazy anchors roll away like tumbleweeds. By war's end, field data from over 50 combat zones feeds back into continuous design improvement. The 1945 production models barely resemble the 1942 prototypes. Better ventilation, stronger fasteners, improved insulation, and dozens of field-tested tweaks that turn a good idea into a masterpiece of engineering efficiency. May 8, 1945, victory in Europe. August 15th, 1945, victory over Japan. The war is over. And suddenly, the U.S. military owns roughly 170,000 Quonset huts scattered across 6 continents, with no plan for what to do with them. They were meant to be temporary, disposable wartime shelters, but something unexpected happens. Nobody wants to get rid of them. Across hundreds of bases slated for downsizing, commanders look around and realize their Quonsets still work perfectly. Cheap, durable, and endlessly adaptable. They're too useful to scrap. The War Assets Administration, tasked with liquidating surplus property, faces a strange dilemma. Demand far exceeds supply. Civilians, veterans, schools, churches, and businesses all want them. Returning GSC is discover a housing crisis waiting at home. Entire families are living in converted chicken coops, garages, and shared apartments. With construction materials scarce and skilled labor exhausted after 4 years of war, the Quonset Hut reemerges now as a lifeline. The government sells them for $1,000 to $2,500. Complete kits ready to assemble. A conventional house costs 4 times that, assuming you can even find a contractor. Federal programs prioritize veterans, and by late 1946, Quonset suburbs began to appear around major cities. In Los Angeles, Roger Young Village houses 750 families in converted military huts. Vetville communities spring up near universities as the GI Bill floods campuses with new students. Adaptation happens fast and creatively. Families add wooden facades to disguise the steel curves, turning military leftovers into cozy cottages. Inside, walls divide the open span into bedrooms, living areas, and kitchens. Windows are cut into the sides, against all engineering advice. But they make the spaces livable. Some even bury the huts halfway underground for insulation, or connect multiple units to form sprawling compound homes. Housing inspectors initially balk, but the shortage leaves no alternative. Cities approve the conversions, and by 1948, entire neighborhoods of Quonset homes dot America. In Portland, Oregon, the Fairview Edition community features 350 Quonset houses, bright paint, front porches, and vegetable gardens softening their industrial origins. Churches follow next. Growing suburban congregations need space fast, not in decades, but weeks. A Quonset costs $2,500 and can host services by next month. A traditional church costs $150,000 and takes years. The choice is obvious. In Levittown, Pennsylvania, the First Presbyterian Church holds worship in a Quonset hut. From 1952 until 1967, dozens of others follow. The acoustics are awful, the look unglamorous, but they work. Some of these temporary churches last 30 years. Schools joined the movement. The baby boom floods classrooms, and districts can't build fast enough. One Quonset hut provides room for 30 students at 1/10 the cost of new construction. By 1950, over 3,000 schools across America include at least one Quonset classroom. Generations of kids learn under the same arched ceilings that once sheltered B-29 crews and medics in the Pacific. The commercial world catches on too. Mechanics, welders, and farmers see opportunity. A surplus Quonset provides wide-open, column-free space, perfect for machine shops, garages, or barns. A small business owner can buy one for less than 2 months' rent in a regular warehouse. The agricultural sector becomes its biggest civilian customer. The Strand Steel Corporation, once a wartime contractor, pivots to making civilian Quonsets for farms, grain storage, equipment sheds, livestock shelters. Maintenance is laughably simple. Hose it off once a year, tighten a few bolts, and it lasts for decades. And with that, a strange transformation takes place. What began as an emergency wartime necessity becomes a permanent part of American life. The Quonset hut becomes a visual shorthand for practicality over pretense, function over form, an invention born of necessity. They appear in movies, photographs, and television as symbols of post-war optimism tempered by austerity. Architects once dismissed them as ugly stopgaps, but by the 1990s, preservationists begin recognizing surviving Quonsets as vital pieces of vernacular American architecture. Several are granted historic landmark status, protected as reminders of a rare moment when military innovation did fade after victory. It quietly rebuilt the nation that created it. Modern disaster zones reveal exactly why the DNA of the Quonset hut keeps resurfacing in the 21st century. When the 2010 earthquake leveled Port-au-Prince, Haiti, global relief organizations faced almost the same equation that confronted U.S. military planners in 1942. Hundreds of thousands of people suddenly homeless, no infrastructure, no time for traditional construction, and an environment that destroys weak shelters within months. The solutions that emerged often echoed the Quonset philosophy, even when designers didn't realize it. Arched steel frames, corrugated panels, prefabricated parts that ship flat, assembly fast, and less long. The underlying formula hasn't changed because the physics and the logistics haven't changed. Today, the United Nations High Commissioner for Refugees deploys refugee housing units, or RHEUs, which are essentially Quonset huts, with 80 years of material science layered on top. Instead of steel, they use insulated composite panels. Instead of bolts, they snap together. But the essence remains: the curved profile for strength and wind resistance, the self-supporting arch that needs no frame, and the flat-pack design that ships anywhere and assembles with basic tools. A two-person crew can raise one in 4 hours, almost exactly matching the 1942 Quonset specs. Over 200,000 people currently live in these shelters across Africa, the Middle East, and Asia. Hurricane engineering has also come full circle. After Hurricane Katrina devastated the Gulf Coast in 2005, structural engineers studied what survived. The pattern was clear. Curved buildings outperformed rectangular ones. Entire neighborhoods of conventional homes were reduced to bare foundations, while a few arched metal structures still stood. This sparked new research into what engineers now call aerodynamic architecture, designing buildings that work with the wind rather than fighting it through brute strength. The result: structures that look strikingly familiar. Once again, the laws of nature prove timeless. Wind glides over a curve, but smashes into a flat wall. The same lesson Otto Brandenburger understood in 1942 still defines resilient design today. The tiny house movement also channels Quonset DNA, whether it knows it or not. Designers searching for maximum space with minimal materials and cost inevitably arrive at the same geometry. The arch. Dozens of modern prefab companies now sell small arched cabins, built from corrugated metal or composite panels, promising affordability, speed, and off-grid durability. Their marketing highlights sustainability and minimalism, rarely mentioning that their modern innovation was born as a World War II military shelter. At the luxury end, high-end architecture firms reimagine the form with glass end walls, wood interiors, and designer finishes costing $300 per square foot. What was once a utilitarian necessity has evolved into an architectural statement, and the military never stopped using it. Modern U.S. and Allied forces still deploy arched shelters in conflict zones across Afghanistan, Iraq, and undisclosed bases worldwide. The materials have evolved: aluminum alloy frames, Kevlar-reinforced panels, integrated climate control. But the logic remains: portable, strong, fast. Some modern versions unfold from shipping containers, expanding like origami into rigid arch structures within an hour. Others can be airlifted by helicopter and assembled under combat conditions. The philosophy that drove Quonset Point in 1942, build strong, ship fast, assemble anywhere, still defines rapid deployment architecture today. And the numbers still make sense. A modern engineered arch shelter provides reliable weather protection for about $50 per square foot, including shipping and labor. Conventional construction, when even possible in a disaster zone, costs triple that and takes months. For humanitarian agencies and military planners alike, the math hasn't changed. Efficiency still saves lives. But perhaps the ultimate echo of the Quonset comes from beyond Earth itself. When NASA and private space companies design habitats for Mars and the Moon, they keep rediscovering the same principles: curved shells to resist dust storms and internal pressure, prefabricated modules that shipped compactly and expand on site, structures that stand without heavy foundations in alien soil. The constraints of interplanetary construction: minimal tools, harsh climates, limited labor, maximum strength from minimum material, mirror the Pacific Theater of 1942 almost perfectly. Different planet, same problem, same solution. When humans finally build permanent shelters on Mars, Their homes may carry the same engineering spirit that began in a Rhode Island warehouse during the darkest days of World War II, when 30 exhausted engineers faced an impossible problem and solved it with nothing but corrugated steel and extraordinary simplicity.